prove that the following function is a valid joint density function. So before we start our proof, let's consider this here. So let's take note that the Taylor series expansion of e to the x is simply the summation of x raised to j divided by j factorial, where j goes from 0 to infinity for any real number x. And so whenever we want to show that a function is a valid joint BMF, gusto lang natin ipakita na it satisfies the three properties of the joint BMF. So for the bivariate case, we have first one, the joint BMF of xy must be greater than 0 for all points xy in a countable collection. Second one, we want to show that for all the points na wala or hindi included dito sa ating countable collection, the value of the joint BMF must be equal to 0. And the third one, when we sum up the joint BMF of xy and small xy, the sum must be equal to 1. So with that said, let's begin our proof. First, we want to show that the joint BMF of xy is greater than 0 at some countable collection. So first, we want to identify what is this countable collection. So in this case, yung countable collection na to, makikita naman natin siya at mahalata natin siya base doon sa indicator function. So itong term na to is multiplied to these two indicator functions that are equal to 1 or that evaluate to 1 whenever yung argument niya is included in the set of positive integers. In other words, kapag yung y positive integer and yung x positive integer, then definitely this indicator function will be greater than 0. First, let's consider the collection A, which consists of all points in two-dimensional Euclidean space, satisfying the condition that x and y are both positive integers. So note that on this region, the indicator function of the set of positive integers evaluated at y is equal to 1, which is greater than 0. The indicator function of the set of positive integers at small x is equal to 1, which is greater than 0. Also notice that since y is a positive integer, it must be greater than 0. And that implies that y raised to any real number is also greater than 0. And aside from that, also notice that since y is greater than 0, that implies that y factorial is greater than 0 factorial, which is just equal to 1. And 1 is greater than 0. And finally, we know that x is a positive integer, so it must be at least 1, which implies that x minus 1 is greater than or equal to 0. And that implies that x minus 1 factorial is greater than or equal to 0 factorial, which is equal to 1. And that is greater than 0. Now, we have shown that these factors are greater than 0. Aside from these, we also want to show that this one right here is greater than 0. So here, notice that e is just greater than 2. And that implies that e raised to e is greater than 2 raised to e. But then 2 raised to e is definitely greater than 2 raised to 2, which is equal to 4. And that implies that e raised to e minus 1 is greater than 4 minus 1, which is equal to 3, which is obviously greater than 0. So now, since we have shown that all of the factors right here will be greater than 0 for all points belonging in this countable collection, then we have shown that the first property of the joint BMF is satisfied. Now, let's proceed with the next property. You want to show that for all points that are not in this region, the value of the joint BMF will be equal to 0. We want to consider what if the point xy is not in that countable collection A. Then that means that the integrated function of the set of positive integers evaluated at x will be equal to 0 automatically. And that's sufficient to show that all of these factors will zero out. That is sufficient to show that the joint BMF at xy will just be equal to 0. Finally, we want to show that when we sum up the joint BMF over all of the elements of this countable collection, the sum must evaluate to 1. So let's take the sum of the joint BMF of xy for all xy belonging in that countable collection A. But remember, the countable collection A that we're referring to ay yung set of all points in the two-dimensional Euclidean space such that each of their coordinates must be a positive integer. So essentially, this sum is just equal to the double summation of the joint BMF and small xy, where x goes from 1 up to infinity and where y goes from 1 to infinity. But now let's notice that when we do it this way, alin ba yung mas madaling i-sum up? Mag-sum up ba muna sa x or mag-sum up muna sa y? So here, ang mapapansin natin, it will be difficult to sum up y first. Kasi if we will sum up y first, paano mo isa-sum up ngayon itong y raised to x minus 1 divided by x minus 1 factorial by factorial? Wala pa tayong result na nakahanap for that type of summation. In this case, mas madali mag-sum up in terms of x first kasi meron na tayong alam na tool na pwede natin gamitin to sum up those terms. So, let's sum up first with respect to x and then with respect to y. And so doing that, we have the summation from y equals 1 to infinity of the summation where x goes from 1 up to infinity of yung term of the sum natin will be this one. That will be y raised to x minus 1 divided by x minus 1 factorial, y factorial, then e raised to e minus 1 raised to negative 1. And so now notice that in terms of x, we have the constants y factorial sa denominator and also this one. So now let's factor them out of the summation. So this summation now becomes the summation from y equals 1 to infinity of e raised to e minus 1 raised to negative 1 divided by y factorial and then summation of y raised to x minus 1 divided by x minus 1 factorial, where x goes from 1 to infinity. As we can see here, ang index natin will be x, and here we have x minus 1. So let's try first to introduce the substitution that u is equal to x minus 1. So let u be equal to x minus 1. So that means when x equals 1, u must be equal to 1 minus 1, which is equal to 0. And so now let's rewrite this summation. So we have the summation where y is from 1 up to infinity of e raised to e minus 1 raised to negative 1 divided by y factorial times the summation where u is from 0 up to positive infinity of y raised to u divided by u factorial. Note that itong sum na to is just the Taylor series expansion of e to the y. So now we can rewrite the summation as the summation where y is from 1 up to infinity of e raised to e minus 1 raised to negative 1 divided by y factorial times e raised to y. Now, tatanggal na natin yung isang summation and now we only need to sum up over y. However, note that e raised to e minus 1, that quantity raised to negative 1 is just a constant with respect to y. So we can factor it out of the summation, and our summation now becomes quantity e raised to e minus 1, that quantity raised to negative 1 times the summation, where y is from 1 up to infinity, of e raised to y over y factorial. So now, notice that this expression right here is almost the Taylor series expansion of e raised to e. However, we should also notice that yung limit kasi nito, yung lower limit niya is y is equal to 1 instead of y equals 0. If we have instead y equals 0, then this is just the Taylor series expansion of e raised to e. So let's try to manipulate this summation so that it looks like the Taylor series expansion of e raised to e. And so doing that, we get e raised to e minus 1 raised to negative 1 times the summation where y is from 0 up to infinity of e raised to y divided by y factorial minus yung first term. So in this case, our first term is just e raised to 0 over 0 factorial. So kaya kailangan natin siyang tanggalin so that in essence, we're just summing up from 1 up to infinity. So that is just e raised to 0 divided by 0 factorial. So now this just becomes e raised to e minus 1 raised to negative 1 times the Taylor series expansion of e raised to e, so minus 1, which is just 1. And so therefore, we have shown that the given function is a valid joint BMF.